Let's take a minute to review the physics of light. We were introduced to some of the basic concepts of this back in Module 2, where we talked about different forms of energy. So now that we're talking about solar energy, which is ultimately the source of so many of the other forms of energy here on the planet, and as we look forward to understanding climate change, let's get a little bit more detailed about understanding what light is and how it behaves and how it interacts with matter. Light is described by a single property called the wavelength. And it's an electromagnetic wave. That sounds complicated. It means that light consists of an electric field and a magnetic field that are interacting with each other and propagating through space. And as a wave, there is a wavelength that describes that wave. The other thing that describes that wave is the speed, but all light travels at the same speed. So the speed of light we denote by the letter c, and that has a value of 300,000 kilometers per second, or 300 million meters per second. And that's the fastest speed that there is in the universe. It's sort of what the universe is built on. And if we had time, we could have some really interesting conversations about relativity and what that means for travel through space and time. But all light, regardless of the wavelength, travels at that speed. As a footnote, if light is traveling through water or glass or a diamond or something like that, then as the light travels through that material, it will travel at a slower speed. But this is the speed of light in a vacuum. We use the lowercase Greek lambda for the wavelength of light, and we perceive wavelength as color. Red is a long wavelength, and blue, if I could be cutesy here, blue is short wavelength, or small lambda, and red is a large wavelength, or large lambda. And the light comes in discrete packets of energy, and those are called photons. And the energy of a photon is uniquely determined by the wavelength of light. It's hc divided by lambda, where h is another numerical constant called Planck's constant. And it's a very small number. C, the speed of light, is a very large number. Planck's constant is a very small number. It's 6 point something times 10 to the minus 27. Let me pause and look that number up for you. 6.63 times 10 to the minus 34, and that's in units of meters squared kilograms per second. We don't really need to memorize that number or anything like that, just giving it there for completeness. But it's a very small number. Even when it's multiplied by the speed of light, a large number, h times c is a small number. The important thing to get from this equation is that the smallest amount of energy that you can have of a light of a wavelength lambda is given by this equation. So if you specify the color of light, I can only have it in packets of energy given by whatever those three numbers work out to if you put them in your calculator, h times c divided by the wavelength of light. The wavelength of visible light is about a half a micron, micrometers, which is 0.5 times 10 to the minus 6 meters, which is 5 times 10 to the minus 7 meters. Width of a human hair is about 100 microns, or about 200 times the wavelength of visible light. So different wavelengths of light interact with matter in different ways, and there are a couple of basic principles that we need to know about the interaction of matter with light. All warm, dense, and by dense here we really mean opaque, objects emit all wavelengths of light. That means stars, planets, people, dogs, houses, trees, anything in the universe that you can't see through is emitting radiation. It's emitting electromagnetic waves, and it's emitting them at all colors. And we describe the distribution of wavelengths of light coming from an object or that we observe with something called a spectrum. And a spectrum is a graph where on the vertical axis we plot the intensity or brightness of the light, and on the horizontal axis we plot the wavelength of light. So an object that has a lot of light in short wavelengths and not as much in the longer wavelengths would look blue to us, while an object that has more light at longer wavelengths and not as much at shorter wavelengths would look red, because that's our perception of wavelength. Long wavelengths we perceive as red, short wavelengths we perceive as blue. All warm objects, warm dense objects, emit light at all wavelengths, and very schematically it looks something like this curve, which we call a thermal emission spectrum. And all light, there's light at all wavelengths, but there is one wavelength where it is brightest. And that's always the case. It's always brightest at one wavelength. And the hotter the object, the shorter that brightest wavelength is. For the sun, that brightest wavelength is right in the middle of the visible part of the spectrum, the color of light that we can see. It's actually, if we could isolate that one specific wavelength of light in sunlight, that is where the sun is emitting its brightest, it's green, actually. So that's a basic characteristic of all objects in the universe. They all are emitting light. Gases absorb and emit only specific wavelengths of light. And those specific wavelengths are determined by the composition of the gas. So some gases, such as carbon dioxide, are transparent to visible light, photons, but are opaque to infrared light photons, the photons that are emitted by cooler objects such as the surface of the Earth, but they're transparent to the photons that are emitted by warmer objects such as the sun. So that's a little bit of a primer on the physics of light and the definition of wavelength and different types of spectra. So for a gas, the spectrum would look like this. The intensity versus wavelength. There might be only a few different wavelengths of light where that gas is produced. So these are emission lines from a hot gas, and whatever gas this is, those specific wavelengths are determined by the composition of that gas. Now, if I have that gas that is cold and light is shining through it, those are the same wavelengths that that gas will absorb from the light that is coming into it.